All right, let's do a surface integral. This is our first look at an example of a surface integral. We're going to integrate the function x squared over the surface that's just the sphere of radius 1. So to do the surface integral, we need the parametrization of the sphere. So parameterize S, and the parametrization looks like our x coordinate will be sine phi cosine theta, y sine phi sine theta, and z cosine phi. This is the parametrization we get from spherical coordinates. We have phi ranging from 0 to pi and theta ranging from 0 to 2 pi for our parameter domains, which are going to become our endpoints of integration. So we need those domains with the surface parametrization. Now we need the tangent vector at any point on the surface, and that's given by, looking at the parametrization derivative with respect to phi. So that is the derivative of this with respect to phi looks like cosine phi times cosine theta, cosine phi sine theta, and the derivative of the z component, the derivative of cosine phi, will be negative sine phi. So that's the derivative. If we put these into a vector r, we take the derivative with respect to the first parameter, we take the derivative with respect to the other parameter theta, and that looks like negative sine phi sine theta, sine phi cosine theta, and 0 for theta. The derivative of cosine phi with respect to theta is just 0. Finally, the normal vector that we need is the cross product between the two tangent vectors. So these are tangent vectors to our surface at any point, the derivatives, and then the cross product gives us the normal vector. And this is worked out. It's a lengthy calculation to do this cross product between these two vectors, and it's worked out in the reading, and it turns out that for the sphere it's just sine phi. After a lot of nice simplifications, which again are in the reading, we end up with sine phi. So what does that mean? Let's clean the board and take a look at what that gives us in terms of a surface integral. All right, we've done the setup work. We did the surface parametrization. We found the two derivatives of the surface parametrization, which are the tangent vectors. We take a cross product of the tangent vectors to get the magnitude of the normal vector, is what is sine phi, not the normal vector itself, but the magnitude is sine phi. And that's what we need for our surface integral. We have the integral becomes 0 to 2 pi in theta, 0 to pi in phi. X on our surface, remember, is sine phi cosine theta, so we're integrating x squared. So that's sine phi cosine theta squared, that's the x squared. And then we have the magnitude of the normal vector, which is sine phi, and then it is d phi d theta. This is the magnitude of the normal vector, the cross product of those two tangent vectors that we found before. That comes out to be sine phi. So that is the integral that we need to compute. We have a sine cubed of phi times a cosine of theta. We know how to do each of those integrals, and we won't do them again, but what you get is 4 pi thirds. So that is a surface integral. The whole process from start to finish is parameterize the surface, get the tangent vectors to it, find the normal vector, look at the magnitude of the normal vector, and then put it all together in an integral. We need the parameter domain to get the endpoints of integration. We replace the variables with whatever they actually are on the surface through the parameterization. And then finally we get to integrate, and in this case comes out to 4 pi thirds.